Hello everyone. Thanks for the introduction, by the way. So I will talk about graph wavelets via sparse cut. So what's the idea here? We are thinking about the graph as something more than just a structure. We are looking at things that are happening on top of graphs. So let's say you can have like some, if you have a water distribution network, right? You might have some contamination that's spreading on top of that. Or if you have a social network, then you have things like influence and information cascades. Or in a road network, right? We have a well-known structure, but you might have trajectories happening in the network, and those trajectories are generating data. And we are looking at how can you represent that data on top of the networks. Our claim is that while we know a lot about how networks look like, we don't know much about how to represent information that's on top of those. And these scenarios are becoming more and more popular. Like if you think about the Internet of Things, you see all these devices like sensors and things like that. They will be collecting data, they will be generating data, and we want to better represent this kind of data. So to be more precise, we are thinking about something like a function that's defined on the space of the nodes. So for each node in a network, you have a value that can be, let's say, an opinion in a social network. And the questions are, okay, if you have data like this, how can you sample it? How can you compress this kind of data? How can you denoise it? These are like very relevant questions that have not been addressed yet. Well, what kind of a nice property you would expect if you see this kind of data? Like one very interesting property that you see in many real data sets is that when you look at data that's on top of nodes, like node attributes, whenever you have nodes that are connected to each other, they would behave in a similar way. So if you have friends, they often will have similar opinions. If you have points that are close by in a road network, the speeds that you see in those points will be similar. And this is actually a very nice property. Like it's very, very easy to understand this sort of property when you think about a function. We know what a smooth function is, right? It's like if you look in positions that are close by, the function doesn't change a lot. But in a graph, you also see this kind of behavior. And when you see this kind of behavior, actually you can exploit this property to have a low dimension representation for the data. So whenever you have smoothness, you can get in some space a lower dimensional representation. And this is very powerful in many, many domains, including machine learning and many others. So okay, where people are very good at dealing with this kind of data that has smoothness and where you want sparse representation. Well, if you think about signal processing, that's basically what they do, and they have been doing this for many, many years. So if I go to a signal processing guy and I tell you, oh, I have this image, can you compress it for me? He can easily do it. He's gonna do some Fourier transform, wavelet transform, or something like that. But what if I give him a graph? Then it's not that easy, because graphs are in a space that's not as well structured as an Euclidean space. So in Euclidean space, you can do many, many things that in graphs are hard to do. Like in a graph, for instance, in an image, I can partition the image in half. But what is a half of the graph? It's not very clear. So the broad goal of this work is sort of like helping in generalizing things that people know how to do for signals that are in Euclidean space that's very well structured to the space of sort of a little bit less structured a domain of graphs. How can we do this? People started thinking about this problem some years ago, and the main approach is called graph Fourier transform, which the idea is basically you can look at the eigenvectors of the Laplacian matrix and try to project your function on top of those eigenvectors. So if you assume that the eigenvectors can capture some structural properties of the graph, and if your function W is smooth, then you capture that using those eigenvectors. The problem is that the same way that Fourier transform doesn't work well in every scenario in signal processing, let's say if you don't have constant frequency, then your Fourier transform will not capture data well. If you have like some localization, or let's say some graph region that has a very different behavior from the rest, then graph Fourier also doesn't work well. So what people did, okay, let's generalize wavelet transform, because we know that wavelet transform can capture this sort of behavior. And here I'm going to talk about one particular way to do graph wavelet transform that's based on partitioning. So this idea that was proposed some years ago is very simple, but is also very powerful. So if I can somehow define a tree that partitions the graph in a hierarchical way, it's very easy to compute a wavelet transform on top of that tree. So let's say I start with the full graph, where I have a single partition, and then I can divide this graph into 2 parts, and then this will give me 2 partitions, and then I can keep doing that until I get to the isolated nodes in the bottom. And someone has proved that if you have a tree like that, you can compute wavelets on top of those, on top of the tree, using that tree as a basis. The problem is, no, okay, so let's give a little bit more detail on this. So this is just an abstract way to understand how wavelets on graphs work. But actually how you deploy this idea is quite intuitive. You just need to find a way to compute some wavelet coefficients based on the partitions. So here I'm showing that if you take up 2 partitions, xi and xj, you can compute some weighted difference based on the values of the nodes that are assigned to those partitions. And that gives you your wavelet coefficient. And more than that, you can compute the energy of that coefficient, which pretty much tells you like how informative that coefficient is, as a way to get some sparse representation. So in the paper, we have proved that this sort of wavelet have a Parseval property. So pretty much what it means is that the energy of the coefficients is equal to the energy of the signal. And whenever you have something like that, what you want to do is to have a few coefficients with very large value, because the other ones will automatically approach to 0. So we have shown how to compute the energy of a wavelet coefficient in the graph. And of course, you can always reconstruct your data based on coefficients. So if you have all the coefficients, you get a complete reconstruction for your data. But maybe if you drop some coefficients that have small values, then you get an approximation that is still good. Just one example. So you start with a graph like this. You have values assigned to the nodes. And then first thing is to compute a tree that partitions these graphs from top to bottom. So in the bottom, you have each individual node in the graph. Now, once you have this tree, you can compute a graph wavelet transform, just using the way I told you how you can compute the coefficients. So, okay, now you have the coefficients. You can forget about the original values. You can completely reconstruct your data just from the coefficients in the same way as in the wavelet transform. But more than that, if you notice here, let's say whenever your values are similar and they are assigned to the same partition, your coefficient becomes very small. So in this case, if the 2 nodes have the same exact value, your coefficient becomes 0. So you can drop that coefficient and you still get full reconstruction. But if your coefficient is not that large, you can still drop it and get a good approximation. So this is the basic idea. So several interesting properties of this kind of wavelet transform. First of all, it's an orthogonal basis, so this makes the reconstruction much easier. Well, if you have a nice tree, which is a tree that captures the smoothness in the data, this will lead to a sparse representation, so you get good compression, you can noise data based on this. And also because like we're in data mining or in graph theory, people like are familiar with this problem of computing partitions in graphs. So it's nice to connect with something that you already know how to do. What are the challenges when you apply this kind of approach? First of all, if your tree is not good, if it doesn't capture the geometry of the data, then your representation will be pretty bad. So if I give you a bad tree that doesn't separate the nodes as well as I told you before, then you won't get any compression. You get you're going to need a lot of coefficients to represent the data. So that's not what we want. But we know that in a lot of data sets, there must be one good tree or one good basis to represent the data, and we are looking for that basis. So to summarize the paper, we have introduced this problem of computing graph wavelet bases using sparse cuts. We have shown that this leads to some low dimension representation for graph data. But we also have shown that this problem has very interesting connections with some existing problems in graph theory, especially partition problems like multiway cuts and graph bisection. And these problems are very hard. We have shown a formulation that leads to a nice algorithm to solve this problem using spectrograph theory. And then we have proposed some ideas on how to make this algorithm scale to some reasonably large data sets. So to formalize the problem, what's the wavelet basis via sparse cut? So I'm thinking about a tree that gives me a partitioning of the graph. And because I'm talking about representation, so I care about the encoding size of that tree. And what I'm calling encoding size size is something like this. If I want to tell you about a cut, the best way to describe that to you is by giving you a list of edges, right? So if you want to communicate a cut to someone, let's say from like a sender-receiver kind of scenario, you just send the list of edges. And we want a sparse cut because then this list of edges will be small, so you can represent that with a small number of bits. Then the problem becomes, okay, if I give you a number of edges, can you give me the best tree? The tree that if I use that tree to represent my data, and then I drop the coefficients that are not covered in that tree, the reconstruction error will be minimized. That's the problem. That's the formal problem. So we have shown that this problem is very hard. It's connected to some hard problems in graph theory. I won't give much detail on this. And then how do we solve this problem? So there is this very, very nice framework called spectrograph theory to solve combinatorial problems in graphs. And the philosophy is very interesting. So you will start with a problem that is probably NP-hard, like a cut problem in a graph. And then you don't know how to solve this problem. So what you do is that you try to generate some matrix from the graph. And then the interesting thing is that in linear algebra, these problems are usually not NP-hard. Like you can do things with matrix in polynomial time. So you solve your problem as using some matrix as some eigenvector computation over those matrices. And then you get a relaxed solution for your problem. And then you go back, you round the solution, and you get a solution for the original problem, for the graph problem. So there is this sort of relax first, solve as an eigenvector problem, then round the solution and get a solution for your original problem. And people have been proving a lot of nice results regarding the approximation that you get once you do this whole process. It's like things like Chigger's inequality and things and other similar results. So we apply the same idea. So you start with a combinatorial problem, a hard problem. We show how to relax that problem to a linear algebra domain. Then we show how to round the solution back and get what we actually want in the first place. So how do you do that? Which kind of matrix can capture both? So at this point, you should be understanding that we don't care only about the graph structure, right? You have some process that's happening on top of the graph. So you need to somehow take into consideration both of them, both the process or the data that you're seeing and the graph structure. So how can you do that? So we have shown that you can use three very simple matrices. In particular, one of them that we're calling S, which captures the dissimilarities between the nodes. And if you combine these three matrices, you can actually represent the energy function that I described to you before. So that tells you how good a wavelet coefficient is. So basically what I'm saying is that, okay, there is an equivalent formulation for the wavelet problem that deals with partitions. In the linear algebra space, you can write that as some quadratic forms of matrices. And this is very interesting because once I can write this problem as a matrix, I can relax that. So I relax the constraints. I say, like, I don't want a discrete solution for the problem because this is still NP-hard. Now I'm happy with a relaxed solution that can be a real value between, let's say, -1 and 1. And then I can take the constraint and I can add it as a regularization factor of my problem definition. And now I have a way to solve this problem using linear algebra. So we show that you can actually do some pretty standard substitution of these variables, and you can define the problem as an eigenvector problem. So look, again, remember that we are looking at both structural information that's given by this Laplacian matrix L, but also information that's coming from the signal that we want to represent. This is in the matrix S. And what's interesting about this formulation is that, well, people have been looking at how to do regularization in graphs, like in machine learning and many other domains, and we have shown that there is a very interesting connection. Like, if you expand this matrix M, that's a result of our transformation, you get some sort of well-known pattern of what people do in regularization graphs. So you have a function of the eigenvector, and then you have a product of the associated, you have a function of the eigenvalue and a product of associated eigenvectors. So in graph regularization, people look at what functions you care about, and what we have found here is that if you want to find a good wavelet basis, there is a particular function that minimizes your error, and that function is just 1 over the square root. So that's sort of an interesting connection with what is already existing in so just to give you an idea how we use this, so basically you just compute those eigenvectors, and then we round back the solution by doing a linear search. So if you sort the nodes in terms of what value you get in your eigenvector, you can do a linear search and find where is the best place to do your cut. And this is one example. So you get a data set like this that has a signal on the nodes, and as a solution of your eigenvector problem, you get a vector that's also of real values, and you just need to find where in your graph should you cut so that you minimize your objective function. So you can do this polynomial time. Now I'm going to talk a little bit about performance. Like we all know that, I mean, although these problems in linear algebra, you can solve them in polynomial time, they are still quite expensive, right? So if you need to do a pseudo-inverse of a matrix, it's a cubic operation, and if you need to compute eigenvectors, it's cubic as well. So this one is scaled to very large graphs. So we didn't completely solve this problem, like we didn't go to linear cost, but we at least reduced the complexity by order of n by using some like some simple ideas, like actually you don't need to look at this constant beta that tells you how much you care about the graph structure. You can just set a constant, and usually the method works well. But there are some more sophisticated ideas that you can use, like someone has shown that you can use something called Chebyshev polynomial, which approximates some properties of the pseudo-inverse of the graph. So we have shown that you can use those same ideas in our problem to compute the wavelet basis. And also, as you probably already know, like when you have an eigenvector problem, oftentimes you can solve it using the power method, so you can do it iteratively. When with a few iterations, you can approximate the solution well. So some results. First question that we ask is like how efficient are these solutions? Like whether our optimizations really get us any benefit. And we have shown that actually, if you do those optimizations that I just described, you can become 100 times faster than the trivial algorithm that is just applying the eigenvectors and compute the pseudo-inverse and all that. So we get up to like 100 times faster, and so Chebyshev polynomials, you have to define how many coefficients you want to keep. We have shown that with only 20 coefficients, you can approximate the solution well. So this gives a lot of gains in performance. Second thing we looked at is, well, we wanted to find one application for this kind of approach, and the application we found that's the most intuitive is compression. So like I told you before, you get a wavelet transform, you get the coefficients, you expect this coefficient to have like a fast decay, like a very few coefficients with high value, a lot of coefficients with small value. So you can drop the coefficients with small value. This gives you a compressed version of the data. Then you want to see how good that representation is, like how accurate it is. So we did that. We compared with some existing ideas in signal processing on graphs, like graph Fourier, other definitions of wavelets on graphs, and we have shown that we do better. In fact, we do up to 8 times better, so we get 8 times lower error than the baselines. So to conclude my talk, which might be too early, I don't know, but the idea is we have proposed this problem of computing wavelets on graphs, and we have shown that you can do that using some ideas of spectrograph theory, and that actually leads to very sparse representations of graph signals in many real data sets. More details, we have shown that the problem is NP hard, even to approximate. And you can find details on the paper and on the proofs. We have proposed a novel algorithm to solve the problem using spectrograph theory. And we have proposed a more efficient version of that algorithm using many optimization techniques. And then we have shown the compression results are better than the baselines. So as future work, we want to study the hardness of some other related problems that arise when you're doing wavelets on graphs. We want to generalize the type of wavelets that we do. So, I mean, if you are a signal processing person, you know that there are different kinds of wavelets. The definition that I told you before just is one possible way to do wavelets. It's called hard wavelets. That's it's like the box function that you have seen probably at some point. But there are other kind of wavelets, like the hat wavelets. So how do you do those things in a graph as well? This is an open problem. And we also want to generalize these ideas for a dynamic graph. So when your signal is changing over time, maybe your structure is also changing. How can you represent those data sets as well? Okay, so thanks a lot.
Yeah, so we have time for a few questions. So go ahead, use the mic.
Thank you, Arlei. Very interesting work. So I was wondering, you said that you can almost find the tree for almost every data set, right?
Yeah.
I was wondering, have you tried like those scale-free graph? Because basically what you show, like the traffic is a road graph, right? So how about like airline traffic?
So you mean scale-free in terms of the structure, the degree distribution?
Oh, sorry, what's it?
You mean like the scale free is in the distribution of the degree,
Yeah,
or the values?
Discrete, distribution is on one side. The other side is like airline. You can like fly all the way from San Francisco to New York instead. So in that case, will the cut-based algorithm work as well? I mean, as good as what you showed?
Yeah, that's a very interesting question. So a lot of people challenge this idea that there are sparse cuts in graphs, right? That you can find communities by cutting some edges. But on the other hand, like we have seen, at least for these data sets, so for the traffic air traffic network, it's a very sparse graph, right? You have like these hubs, and then so at least I believe, based on my intuition, that for those graphs you can still find some sparse cuts, right? Because if you take, I mean, you don't want to cut a hub, but you take some, you have sort of hierarchical structure, right? Like, and then if you can find the border of the hierarchy, it should be sparse, right? Because most of your
Okay, you mean the bottom hierarchy? I see, like the low region, all those kind of.
But patterns. Yeah, but maybe it's not as sparse as a road traffic network, right?
Exactly.
But but that's a very interesting point. Maybe we have access to some air traffic data, so you can try and see whether there is some good cuts there as well.
Right. Yeah. Thank you.
Thanks.
Okay. So any other questions? Okay. If not, let's thank the speaker. Okay.